So this is a session on homomorphic encryption and arithmetic. And we have 3 papers. The first paper is presented by Loris Bergera. Loris, please.
Can you hear me? Yeah, okay. Okay, so hi everybody. I'm Loris Bergera, and today I will present you the work TFHE gets real, an efficient and flexible homomorphic floating point arithmetic. This work is done in collaboration with Hilaria Chilotti, Damien Ligier, Jean-Baptiste Orfila, and Samuel Tapp. Okay. So before starting with homomorphic floating point, I will make a brief introduction of FHE and TFHE. So, as you already know, fully homomorphic encryption is a family of encryption scheme which permits to perform operation over encrypted data. So, for instance, in this scheme, the client can encrypt his data. He sends it to the server. The server can perform some operation over this encrypted data, and he sends back the result to the client. And the client can decrypt the message. So so in this scheme, as you can see, only the client can encrypt and decrypt the ciphertext. Okay. So in TFHE, the security relies on the LWE assumption, so learning with error. So we have LWE ciphertext. An LWE ciphertext is composed of a secret key, which is a vector composed of a binary value, a mask, which is a vector composed of random value, and an error, which follow a Gaussian distribution. From there, a ciphertext is composed of the mask, so the random vector, and a B part, which is equals to the dot product of A times S plus delta M plus E. So the part delta M plus E can be represented like that. So you have the error on the less significant bit and the message on the most significant bit. So the message is shifted by the value delta. Okay. So in TFHE, we can perform many basic operations, such as the addition or the multiplication by a constant. When you perform an addition, you need to add each element of the mask, add E together, and you obtain a new ciphertext that encrypts M1 plus M2. So this operation can be represented like that, and as you can see, when you perform an operation, the message grows, but you have also the noise grow. So here in this example, when you perform the addition, you have the result of M1 plus M2, but you have also the result of E1 plus E2. So it's a problem because all along the computation, the noise will grow. And if there is too much noise, the noise will overlap the message, and we cannot decrypt correctly the message. So to answer the correctness in TFHE, we need to manage the noise during the computation. To do that, we have an operation named bootstrapping, PBS in short, which takes in input a noisy ciphertext, a bootstrapping key, and an univariate function represented as the lookup table. And the PBS permits to perform, to evaluate the message M with these univariate functions. And moreover, when you, as you can see on the right, after the PBS, the noise decreases. So this operation is very efficient, but only for small message. So let's say smaller than 10 bits. So okay, it's an operation that reduces the noise and permits to evaluate any univariate function. Okay. So in TFHE, there is other operation and other ciphertext. So we have already seen the LWE ciphertext, which is represented by a blue box, but we have also other ciphertext, such as the GSW ciphertext, which can be seen as a collection of LWE ciphertext. So that's why it's several blue squares. Okay. This ciphertext permits to perform other operations. So for instance, we have the external product, which permits to perform multiplication between two messages. So here we have M1, which is an LWE, encrypted in the LWE ciphertext. We have M2 encrypted in the GSW ciphertext. And we can perform an external product, which output the product of M1 times M2. There is an operation named circuit bootstrapping, which permits to transform an LW ciphertext into a GSW ciphertext. It's a costly operation, which is done by performing several PBS and other costly operations. But yeah, we can transform an LW ciphertext into GSW ciphertext. And from there, we can perform more complex operations that will be useful in the rest of the talk, which is the CMUX. So the CMUX taking as input two LW ciphertext and a GSW ciphertext, which encrypt a bit, 0 or 1. And it permits to choose between two ciphertexts. So for instance, here in this example, if B is equal to 0, the CMUX will output M0. Okay. So in TFHE, there is several limitations. We have already seen that we can work only on small message space. We can naturally represent small integer, and we have no information during the computation. From there, currently, we can only represent integers and fixed point with CHES and TFHE. And we want to reach more larger range of value. And one of primitive data type which are not represented with TFHE is the floating point. So the question was how to efficiently represent floating point number with TFHE. Okay. So let's start with the homomorphic floating point. Okay. So in clear, a floating point is represented with 3 values. You have 1 bit for the sign, several bits for the exponent, and several bits for the mantissa. In the case of 8-bit floating point, you have 4 bits of mantissa and 4 bits of exponent and 3 bits of mantissa. You have another value, which is the bias, which permits to determine the range of the floating point. So where you put the point of your value. Okay, so a floating point follows this encoding. So you have the sign which determine if your value is positive or negative. The exponent, which permits to determine where is the point, and the mantissa, which gives the precision of the floating point. So for instance, we can have this floating point, which is encoded like that. Just in the following, I will add the black one just to explain some stuff. It will be more clear, but yeah, in the floating point, this value is not present. And yeah, with this example, we obtain this floating point, which is equal to 0.6875. Okay. So now, how can we represent this value with TFHE? So the first idea is to have one ciphertext to represent the sign, and several ciphertexts to represent the exponent or the mantissa. So let's say that an LW ciphertext can encrypt 2 bits. We have this representation. So as you can see, we have 4 bits for the mantissa with this representation. Yeah, it's because we have parameter which permits to work with 2 bits and is the same cost with this parameter to work with 2 bits or 3 bits. So yeah, we have 1 more bit of precision for the mantissa. So with this representation, we have fast operation for medium and large precision. And we can support many of the classical operations, such as the addition, the subtraction, multiplication, division, yeah. And so in the following, I will just present how to perform an addition. Okay. Okay, so first, how can we perform an addition in clear with floating point? So suppose that we have these 2 floating points. The first step is to find which of the exponent is the biggest, and especially which one has the biggest exponent. Because as you can see here, the 2 exponents are not equal, so that means the mantissa doesn't represent the same thing. So the first step is to align the mantissa. So for that, we check the 2 exponents. We can see that the exponent on the right is smaller. So we add +1. So we make increase the exponent. Like that, we have the same exponent. and we shift the mantissa to keep the same value. As you can see, the real value is not exactly the same because when we do that, we lost 1 bit of precision in the mantissa. Okay, so now we have the same exponent, so we can add or subtract the mantissa regarding the sign of the floating point. Here the two signs are not equal, so we subtract the mantissa. And finally, you see that at the beginning we have a representation of the floating point, and especially we have the black value, which is equals to 1. So the next step is to normalize the result. That means we want a 1 in the black value. Okay. And for that, we shift the mantissa to the left, and as we shift the mantissa to the left, we need to decrease the exponent. Okay. So now the question is, if we have two homomorphic floating points, how can we align the mantissa, add or subtract the mantissa, and finally normalize the result to obtain an homomorphic floating point, which represents the addition of the two input homomorphic floating point. Okay. So the first step is to align the mantissa. To perform this operation, we only need to have the mantissa and the exponent of the two floating points. So the first step consisting in subtract the two exponents. From this subtraction, we will obtain sign, which determines if E1 is bigger than E2 or 2 is bigger than E1. And we will transform this sign with circuit bootstrapping to obtain a GSW ciphertext, which encrypts the sign. We do the same for each bit of the subtraction between the two exponents. So we have a decomposition of the result of the subtraction by bit, and each of these bits is encrypted in GSW ciphertext. So from there, with the sign, we can choose between M1 and M2 regarding the value of the sign, and we can choose between the two exponents, E1 or E2, to output the biggest exponent between the two exponents. Okay. So from there, we want to align the mantissa. So taking the output of the first flux, we will choose either between the mantissa or between only the LWE containing the most significant bits. As we work with two ciphertexts, we need to add ciphertext which encrypt 0 to have the same representation. And from there, with this, the first bit, we can choose between two mantissa. And we continue like that for each bit, and at the end, we obtain an aligned mantissa which is aligned, and the biggest exponent between E1 and E2. Okay. So the second step is to perform the addition or the subtraction between the two mantissa. As we have no information during the computation, we need to perform the addition and the subtraction. First, the addition. With the addition, we will output 3 LW ciphertext, because when you perform an addition, you may gain 1 bit of precision. So yeah, we need to represent this biggest value. And we perform the subtraction, and with the subtraction, we can obtain the mantissa plus sign regarding if M1 is bigger than M2 or M2 bigger than M1. As add mantissa output 3 LW ciphertext, we need to have 3 LW ciphertext after the subtraction. So we add a new ciphertext which encrypts 0. From there, we can sum the two signs, S1 and S2, and transform the result into a GSW ciphertext, and each permits to choose between the addition or the subtraction, regarding if the two signs are equals or not. Okay, and yeah, of course, this operation permits us to choose the sign of this operation. Okay. So finally, the last step, we want to normalize the result. So as in classical floating point, we want the same representation as the input, and here you can see that we have 3 bits of the mantissa. So the goal is to take the most significant block of the mantissa, transform it into a GSW ciphertext, which encrypts 0 if the result is equal to 0, or 1 if it's equal to something else. And from there, we can choose between the two less significant blocks which represent the less significant bits of the multistar, or the two most significant blocks. And accordingly to this bit, we need to change the exponent, so add +1 if we take only the most significant block. And we can output floating point ciphertext, which have the same representation than the input ciphertext. Okay. So in this work, we have done all the basic operations, so the addition, the subtraction, multiplication, and division. We have also performed more complex operations like sigmoid and ReLU, and cosine and sine by using Maclaurin series. So for each operation, we study the noise propagation, the failure probability. So yeah. So yeah, to conclude, with this representation, we obtain this result. So on the left, you have the sequential timing. On the right, the parallel Y. So it's for 32-bit and 64-bit floating point. And yeah, as you can see, we obtain a speed up between a factor 6 or a factor 100 compared to the previous state of the art. So yeah. So in this work, the homomorphic floating point uses the radix representation to represent large integer for the exponent and the multistar. It's mainly based on the circuit bootstrapping and CMUX, which is a costly operation, but as we use the result several times, it becomes more efficient. And yeah, it's relatively fast for medium and large precision. In this work, we also study another representation, which works with the BBB plus UPBS. This representation uses only one algorithm for all the operation. It's very fast for small precision, but yeah, it doesn't work for large precision. So yeah, as I said, we have studied the noise propagation and failure probability for each of the operation. It's not real time compared to classical floating point, but yeah, as we can see with the timing, we close the gap compared to the previous work. We can support plus, minus, and not number values. And yeah, as a future work, we want to implement this value because it's not implemented yet. We want to combine the two techniques, so the one with the UPBS and the one that I've presented, to have the strength of the two techniques. And finally, any improvement on the circuit bootstrapping or the PBS will lead to an improvement to this representation. Yeah, thank you.
Thank you. We have time for a few questions. The microphone is there. Really nice slides, by the way.
Thanks. I don't even have to move to the microphone. So I was wondering the Maclaurin series. Why use floating operations for that and not use the Cordic algorithm or something like this if you're going to build it out of lookup tables?
So yeah, the idea to use Maclaurin series is that you can perform addition, subtraction, to have the result of more complex operation like cosinus, sinus. And yeah, the question is why we cannot apply lookup table to perform more complex operation. That's it, yeah. Because in the classical PBS, you take only one input, ciphertext. Yeah. If you want to evaluate more large lookup table, you need to take. You can use operation like the UPBS or BB+ is the idea to evaluate more complex operation. But to perform this operation, you need to take all the input, all the ciphertext as input, and you may end with a large, very large lookup table, so it becomes inefficient, and it doesn't work for large precision. I don't know if it's clear. Yeah.
Thanks.
More questions? be shy. So maybe let me meanwhile ask you about, so you mentioned in your slides not a number representation, infinity representations. And so that brings to mind exception handling, right? Like you have a division by 0, that would be an exception. But exception is not regular data flow. That will require some modification to your scheme, which is, do you have any thoughts on how to handle exceptions?
So represent plus infinity and minus infinity? Yeah. Basically, you have the problem with plus and minus when the exponent becomes large. And the idea is to create a new ciphertext that follow this value if at some point the exponent becomes bigger or not. And yeah, it represents plus and minus. And yeah, of course, we have seen when we perform an operation, we need to perform operations. In addition, you need to perform the subtraction and the addition. So you may reach the infinity addition, but not with the subtraction. And at the end, you choose the subtraction. So we can also choose this value, plus. But yeah, of course, floating point arithmetic is really complex, and there is a lot of problem, and all these small things are not all over the place.
Right. Yeah. That's why it was in your future workbook.
Yeah. Of course, we have the idea, it works. Yeah. But yeah, there is also another.
Thank you. Vincent?
So you showed us an example with 8-bit floating point, and I understood your results to say you could do 16-bit, 32-bit, 64-bit. What I'm wondering is, as you increase the number of bits in the floating point representation, the number of operations you have to do increases, usually by the square at least. So did you compare the number of bootstrapping operations needed for smaller versus larger floating point numbers, and did you see a large growth?
Yeah, of course, the more floating point is big, the more we need to perform bootstrapping. But when you look the floating point representation, when you go to bigger representation, you can see the exponent, and the exponent not grows so much compared to the mantissa, which become larger. And for instance, if I take the addition, you have seen that the costly part is to align the two mantissa, where we subtract the two exponents. And so if you go from 8-bit floating point to 32-bit floating point, I don't remember, but yeah, you have only maybe 1 or 2 bits more for the exponent. So the costly part is to change the LW ciphertext into GSW ciphertext. So yeah, you increase the number of circuit bootstrapping, but not that much. And at the end, as you reuse the result of the circuit bootstrapping several times, the cost, is not in square compared to the number of bits.
Great. Yeah. Oh, last question? Okay, go ahead.
Sorry, I missed the talk. I was late. But I have one question to ask. It's always a question for myself. Because I was a big fan for CKKS, so I'm wondering, it is great that TFHE can be used for real number as well. So how is the performance currently compared with the CKKS when it comes to the real number computation?
Okay. As presented at the beginning, with CKKS, and here we can represent a fixed point. Okay. And here the goal is to represent floating point. So yeah, I don't know if it's really, we can compare with the floating point and fixed point. I think we have better result with fixed point, but we cannot have all the, we cannot represent all the values that we can represent with floating point. Yeah. I mean, it depends on the use case as any, yeah.
Thanks.
Let's thank the speaker. All right, our second talk is actually on CKKS and will be presented by Jae-Hoon Kim. Slides. Do you have the clicker?
Hello everyone, my name is Jae-Young Kim, and I'm going to talk about my work, Efficient Homomorphic Integer Computer from CKKS. So very brief two-line summary of my work. So like we mainly focus on integer arithmetic, but with like a wide number of instructions like addition, multiplication, bit shift, and comparison, and I want to do this in an encrypted world. And we design a dedicated fully homomorphic encryption scheme using the recent development of a so-called discrete variant of CKKS. So as you may all know, fully homomorphic encryption is a powerful cryptographic primitive, allows you to compute in an encrypted state. So as a basic example, you can imagine there's a client and server, and client wants to do outsourced computation, but to protect the privacy of the data. So to do this, client can first encrypt the data under fully homomorphic encryption, send it to the server, and in the server side, somehow without knowing the underlying data, they can compute whatever function, let's say f, and get an encrypted version of fx, and then send it back to the client, and client can decrypt it and get the desired results. So in the main motivation of our work is integer computer. So you can imagine whatever computer, desktop, server you have, these modern computers all have unsigned integer instructions. And there is a concept of word size, 32-bit or 64-bit, and you have addition, multiplication, shifting, comparison, and these instructions work as a kind of a basic unit operation for the entire a complex integer operations, and it is kind of important to have an encrypted version of it so that we can use it in the encrypted world. And it seems that the CGGIDM community or the TFHE community already has a good playground on this. So I borrowed this table from Zama's TFHE-RS benchmark, which I accessed a few days ago. So they have bunch of integer instructions, not only addition and multiplication, but also different sets of instructions, and also they support many different integer size, 8 bits to 128 bits. And so these days, when a researcher or someone who wants to use build integer application upon FHE, they go to Zama's library and use their APIs to build application. And the main motivation is to emulate or repeat this success in the corresponding SIMD FHE world, like BGB, BFP, CKKS. So to summarize the research goal, the goal is to construct an easy-to-use and efficient integer computer for SIMD FHE. And what I mean by easy to use, first, we require that there's no bootstrapping outside of operations. What it means is that typically in like TFHE, like bootstrapping is like mostly included in like the form of programmable bootstrapping, and like you don't have to worry about like scheduling like difficult bootstrapping outside of it. So like we wanted that good characteristic, and also we require universal encoding structure for all the operations. I mean, it could be that like there is a multiple encoding structure with it good at different operations, and there are expensive conversions between it, but like we don't want it, so like we wanted to avoid it. And in terms of efficiency, we mainly target throughput, which is defined as amortized latency, and it is basically a latency divided by the number of slots. And before talking about our scheme, like we can first think about like if you want to do integer arithmetic, which FHE scheme to use. And to understand the current landscape, there are mainly 3 different families of FHE schemes. So there is a BGB VFE family, like CUG IDM family, and CKKS. And the biggest difference between them is whether they support SIMD or not in the plaintext space. And when you first look at it, you might just wonder that, oh, BGB VFE naturally supports integer, and why not choose like P to be like 2 to the 32 or 2 to the 64 and use BGB VFE. And the problem is that first, there are 2 problems. First problem is that the noise growth is proportional to the plaintext size, and it like significantly affects the parameter, especially you want bootstrapping. And like the second problem is that it makes it hard to like support various operations like comparison, like bit shift, and so on. So like then the natural way to do this is to do a radix style or like digit decomposition based approaches. But even in that case, there is a problem of BGB VFE that the parallelism is limited. So for instance, you can imagine a like modulo 2 to the k BGB VFE, then due to the number of theoretic properties, it can only support up to n over log 2 of n slots, which is much smaller than which CKKS can support with at most large n. So instead of using BGB VFE, we use the recent development of discrete CKKS. And for those who are not familiar with this, like this was first suggested in the Bleach papers presented in like Journal of Cryptology 2024. And like in the last 2 years, there are a lot of like improvements in this scheme. And to like highlight the biggest difference between discrete CKKS and other schemes, I would like to like mention how message and error are distributed in this new paradigm. And in BFE, as you know, messages are put in the most significant bits, and like errors are put in the least significant bits, so that they are naturally separated and like becomes an exact scheme. And CKKS, and somehow like both of them are in the least significant bits, and message is kind of always contaminated by the error, but it is kind of okay because like at least some of the most significant bits of the message is preserved. So like CKKS works that way, and discrete CKKS is kind of a hybrid between the two in the sense that there's a clear separation between message and error, but like message is put somewhere between MSB and LSB so that it can also support like good characteristics like DFT encoding and like characteristic 0 multiplications. And for black box usage of discrete CKKS, it supports the following homomorphic operations. The first type is arithmetic operations, which are basically addition and multiplication over z, and they are like directly inherited from the original CKKS. And the second type is lookup table or functional or programmable bootstrapping, and it allows you to evaluate any function f from zt to zt, where t is a small integer, like you can imagine like 8 bits. And there is also a modular reduction, which allows you to take modulo t operation by a small integer t. So like in this presentation, I want to keep everything very at high level so that you don't need to understand the inner details of like discrete CKKS. So you can imagine there's a homomorphic computer or kind of a restricted version of computer that allows only like addition, multiplication, and modular reduction. And the computer is equipped with a SIMD structure or vectorized instructions. for a large dimension n. You can imagine something like 2 to the 15. And so like in the operations work element-wise. So in this example, it's the element-wise multiplication, and 7 is multiplied by 1, 3 is multiplied by -2, and so on. And the important restrictions of this computer is that computer only supports up small integers, let's say up to 8 bits. So you cannot put the entire like 32 or 64 bit into like a single ciphertext, and you somehow need to like divide it into chunks. And also modular reduction is much more costly than other operations because it involves like discrete bootstrapping, and it is important to minimize the number of modular reductions. So to do this, we just like divide large integers, represented in like a digit style format. So we can write in base D digit format. So for instance, in this case, A is represented with 5 digits, A4, A3, A2, A1, and A0. And like to do this, we have like different ciphertexts. Exactly 5 ciphertexts representing individual bits. So like large integer vector can be represented these like 5 vectors, and because they are just SIMD, in this talk you can just imagine that they are just like 5 digit, and we want to construct a computation with these digits. And like among the different operations, perhaps the most difficult one is homomorphic multiplication because it involves the most like complicated format. And the main question is to how to multiply while minimizing the number of modular reductions. And there seems to be a straightforward answer, which is textbook multiplication, but in convolution style. So what is this? Well, like, let's say we want to multiply 2 integers, a and b, written in like a digit decomposed format. Then like we start from like the lowest digit, the LSP, and like construct 1 by 1 from the lowest digit. So how it works, you first compute the like product of the lowest digit, A0, B0, and divide it by D to get quotient and remainder. And the remainder, R0, will be the lowest digit of the product. And then Q0 is kind of become a carry and go to the like first digit. And in the first digit, you need to evaluate A0, B1 plus A1, B0 plus Q0. And like again, you would divide by D and get like carry and remainder. And this repeats again and again. And like in the ith step, you will be basically like evaluating convolution and like carry and just take modular reduction repeatedly. So in this like algorithm, there is U modular reductions for U digit numbers, and this is roughly how it works. And like, but when you go into a little more detail, then there are problem of like modular consumption. So when computing the quotient, you need to like first subtract remainder from the value and divide it by D, but like dividing by D consumes some modulus. So, and if you just do this naively, then the parameter increases significantly, and we don't want to like increase the parameter. So to solve this, we bootstrap some of the CIs using the iterative bootstrapping from KN25. And for instance, like we can support at most D to the D modulus for base D with like 3U minus 2 discrete bootstrapping. And to concretely understand this number, you can imagine like choosing D equals 16, and you can support at most 64-bit multiplication with like 46 discrete bootstrappings. And since we solved multiplication, other operations follow relatively easily. And addition and subtraction are kind of almost the same because you can just do digit-wise addition, subtraction, and like reduce from the lowest digit as before. In comparison, there is a like nice observation is that it's kind of an extended subtraction. So you can add 1 more digit in front of MSB, and just extracting it gives you comparison. And bit shifts are just like looking at the digits and like properly do rotation and like reductions. And also, our scheme supports arbitrary functions because it is like naturally compatible with multivariate interpolation style functional programmable bootstrapping in AKP25. And as a summary, we have an encrypted integer computer supporting like addition, multiplication, comparison, bit shifts, and arbitrary function, and possibly a more wide range of operations. We check our algorithms with experiments. So all experiments are in single-threaded CPU, and we mainly compare with TF-HERS because we are kind of a SIMD version of them. And for 64-bit operations, we are roughly, the latency is much worse, but like the amortized latency is roughly 2 to 3 orders of magnitude better. And if, for instance, for homomorphic multiplication, the amortized latency is like 2,800 times better. And also you might ask, like, what happened if you change the size of the integers? And the observation is that our complexity mainly grows almost linearly in the size of integers because the modular reduction is the bottleneck, while like TF-HERS grows slightly more than linear, so that our method becomes preferable for larger integers. And before I finish the presentation, there is a slightly longer kind of conclusion. So to summarize, we like design a good playground for unsigned integer computations, I mean for SIMD version, on top of like the recent development of discrete CKKS. And I thought CHES is a great opportunity to present because we seek for like systems, hardware level like approaches, like dedicated compilers, like optimizations, and like a new community platform, or etc. And since we achieve like good throughput, a natural question is like, can we achieve better latency? And our recent works show that this, and the answer is quite positive. So for instance, our Crypto25 paper used nested CRT to get like better latency within a single, asymptotically better latency within a single ring of the B ciphertext. And my recent work uploaded on ePrint, like used intermediate encoding between slots and coefficients encoding to get even better results. And notably, we achieved like in homomorphic 64-bit multiplication faster than TF-HERS in terms of latency, not in terms of throughput, and retaining like 3 orders of magnitude better amortized latency. And this is kind of an add-on to this CHES paper. So like it is fully compatible, and you can use like as like an accelerator, and we expect that there will be more add-ons to come later. And as a final remark, it is kind of an important milestone for SIMD version of CGGIDM in the sense that the main ingredients of TF-HE community is like functional programmable bootstrapping and integer computations, and both are quite covered in our recent works, and kind of we are ready to like support a bunch of like works that are done in TF-HE in our SIMD version. This is the end of my talk, and thank you for listening.
Thank you. All right, questions?
Thanks for the wonderful talk. I'm interested to know that how the comparison can be done in your discrete CKKS, and whether this is because I think the comparison is very important to compute the ReLU for machine learning applications. Yeah.
Oh, I see. You mean homomorphic comparison to?
Yes.
Like,
Yes.
I see.
Yes.
So I think I would like to mention the so-called discretization framework. So it was in our earlier work, a paper called Modular Reduction in CKKS, and there we introduced some kind of a framework to like convert CKK ciphertext into a discrete CKK ciphertext, and after that you can use like CKK style functional programmable bootstrapping to compute like discrete function, as you mentioned, like comparison or other type of functions. And I think this framework would be useful when integrated to like privacy preserving machine learning or so.
Does that mean it has to go through the original CKKS and then the discrete CKKS? Or can we just directly use the discrete CKKS?
I think the main problem is that in CKKS the data is more like a fixed point representation, and you somehow need to convert it to integer type, right? So like you need to somehow cut the least significant bits, and like what I mentioned as the discretization framework is exactly how to do in CKKS.
Okay. Maybe I'll ask more offline.
Oh yeah, sounds great.
More questions?
Thank you. Do you provide C codes to play around?
So currently, I don't have like C or C++ implementation, but I would like to refer to our Crypto 2025 implementation because like it involves like most of the ingredients of this paper, and like it's more like an add-on to this paper. So yeah, maybe you can talk offline about codes.
All right. That's why you present at CHES, right? You want us to implement.
Yeah,
Yeah.
exactly.
So can I ask a question on your slide number 13?
Yep.
Because so I was wondering if I understand your SIMD concept correctly. So you're suggesting here that you are going to do your computation per digit, right? And but to compute these partial products here, you see that you need more work for the higher order digits than for the lower order. For example, for the first one, I need one multiplication, A0, B0, but then for the second one, I already need two. And so there's a non-constant amount of work over the entire product.
Yeah, you're very right. And so the complexity looks like quadratic, and like, but the main main issue is that like the modular reduction is a bottleneck. So like modular reduction is, I would say, like kind of 1,000x more expensive than multiplication. So like these quadratic size multiplication is kind of hidden inside like modular reduction. So if you increase like maybe you want to achieve like 1,000 beats of like integer multiplication, then I would quadratic would be a problem. But before that, like modular reduction becomes a bottleneck here.
Got it, thank you. All right, questions? All right. Okay, thank you very much.
Thank
Let's
you.
thank the speaker. We're now going to the third talk. The third talk here is by Johannes Mono.
Thank you. Good morning. I will be talking about BGV-like schemes, which is BFV, BGV, CKKS, and key switching in particular. This is work that started at Ruhr University Bochum, and I'm still a PhD student there, but started doing an internship at Crypto Lab in Korea, where I finished this work. And so they supported my trip here, so thank you for that. And yes, let's get on to fully homomorphic encryption. I'm sure you're familiar with this. We have a client and a server, and we are mostly interested in key switching, which happens on the server side. And this is our underlying mathematical structure that we have to deal with. We have a polynomial ring with degree n and a ciphertext modulus q. And our ciphertexts are essentially two elements in this ring with a secret variable. And all the arithmetic we do is within this RQS ring. And when I was preparing this talk, this is how I felt. This is one of my favorite Korean letters that I got to know. It's the letter U. You can use it as an emoji. It's a crying emoji. Because this is the math I would have had to explain to you when I wanted to explain key switching. I did this in an FHE.org talk. It took me about 20 minutes. I have 20 minutes for my full talk here, so that kind of doesn't work out. And so I decided I have to make a decision. Do I either explain this, or do I simply present you with facts and tell you you have to believe me to some extent, and you go to the paper and check the math to verify that I'm not selling you any snake oil here. And so we go with option 2. You don't have to suffer through math after the rump session, at least not through too much math. But you will have to believe me to a certain extent. So what do we do? What are we interested in? We are interested in key switching. And essentially what key switching does is it takes one of these ciphertext polynomials, Ci, under a secret variable s prime, and it transforms it into another ciphertext equivalent at the cost of an additional error, and obviously at the cost of the computations that we have to do. And the way we do this is using the residue number system. We've heard about this in the keynote as well yesterday. And essentially the idea is we work with rather large bit sizes, so we split this up so that we can work on native integer sizes. And essentially the important letters that you have to remember for this talk are the polynomial degree n. We have a number of primes in Q, that is L. We have a number of primes K in P. This is our extension modulus that we use during key switching. And then we also use a number of decompositions, which here we use omega. And we have this relation between the number of decompositions and the prime sizes, that omega is roughly equal to L divided by K. And so with this, we can analyze key switching. That is the idea. How complex is it? Which parameters do we want to use? And so on. And one thing to note is this obviously has an impact on security. We're talking about modulus, we're talking about degrees. And so if we choose a larger modulus, QP, in general, we are less secure. And because of the relation between the number of decompositions and the modulus, a smaller omega, or a smaller number of decomposition, also means we are less secure. And if we choose a larger degree n, then we get more secure. So we can compensate for a larger modulus with a larger degree, and in this way we can always find a secure parameter set, essentially. And there are two relevant, or there are a few more, but these are the two mostly relevant works on this. One is by Kim, Polyakov, and Zucker. It's called Revisiting Homomorphic Encryption Schemes for Finite Fields. They focus on something completely different, but everyone I talked to who had to implement key switching was like, read the appendix of this paper. Yeah, that's the general recommendation, because in there they provide an extensive summary of key switching, all the variants, and also some computational analysis. But they don't extend this to a complexity and parameter analysis, so this is one improvement that we spotted. And one thing that is also in this paper is an implicit assumption that all our primes are roughly the same size, so that the ciphertext primes and that our key switching primes are roughly the same size. And that can be true, but it doesn't have to be true, especially in BGV and CKKS, where the prime size matters for correctness over the course of the computations, because they influence the noise growth quite significantly. And so in BGV and CKKS, this assumption doesn't necessarily hold, and so it is also important to take this into account when analyzing key switching. And there was another work at Crypto 23 by Kim Lee So Song, accelerating HE operations from key decomposition techniques. And it's an algorithmic key switching variant, and it adds another number of decompositions over the modulus QP, and this is going to be omega tilde. And essentially, it's in this paper, they take a not necessarily an optimal perspective on the asymptotic complexities, and we will get to this. And as a result, the comparison between the two techniques is also a little bit skewed. And so what we do in our work is essentially we take a different perspective on the asymptotic complexities for both of these techniques, so for the original one and for the double decomposition technique. We also provide a comparison, an updated comparison based on this with different parameters. And we introduce novel constant foldings to reduce the multiplicative complexity. We provide analysis for arbitrary input and output domains. This is related to the NTT domain. So we do fast polynomial multiplication with the number theoretic transform. And essentially, for the most part, we assume that our inputs and outputs are in the NTT domain. But there are exceptions, and we essentially provide a more generic analysis for this. And then we also provide practical suggestions to actually achieve that Qi mostly is equal to Pj, so that we have roughly an equal size and our analysis actually holds. And in the end, we provide slightly opinionated parameter guidelines. In this talk, we will only focus on the perspective of the complexities and also the corrected comparison, as well as the guidelines at the end. For the rest, I would suggest you take a look at the paper, as it involves quite a few finicky details of key switching math, and as we already talked about, I'm not going to go into this today. And so what is the previous perspective on key switching for the original key switching algorithm? Well, the idea was always, okay, we fix the degree and the ciphertext modulus so that it's secure. And then we have like a certain amount of modulus left that we can use for P. So our number of primes in P is limited as a constant. And essentially, by extension, we have to choose the number of decompositions in like complexity L. And this, if we look at the computational complexity that is dominated by the number of number theoretic transforms, we can see if we just plug in these asymptotic complexities, we get a squared computational complexity. And the same is true for the key size, right? If we plug in the L there, then we also get a quadratic complexity. And essentially, our argument that we're making in the paper is this is a somewhat incomplete perspective because we can also incorporate the actual complexity of the computations itself and the polynomial size. So if we incorporate the degree, we get a more accurate asymptotic complexity where we get omega L n log n instead of L squared, and we get omega L n instead of L squared as well. And interestingly, if we just look at key switching in isolation, there's actually a threshold where once your number of decomposition becomes too large, it actually makes sense to increase your degree to get better computational and or memory complexity. And this is very counterintuitive. The advice is always never increase your degree, right? And it turns out, if we look at it, at least from a theoretical standpoint, that is not necessarily true. And so another thing that is to note is even if we assume like a fixed n and q, previously the advice floating around was mostly like, well, 3 to 5 seems to work pretty well experimentally, but we don't really know. And if we look at this way, we can clearly see that choosing the number of decompositions as small as possible, so staying within the secure parameter range, is the best approach. A slightly alternative way to phrase this is to say choose P, or the number of primes in P, as large as possible. But we don't gain anything from this if we choose it too large. So the slightly more accurate way is to use the number of decompositions as like a rule to remember. But due to the way they are related, both of them kind of work if you want to remember the other one. And so we also extended this perspective to the double decomposition technique, and we estimated the number of primes in there, and also plugged in all of the formulas. And these are the complexities we get in the end if we also consider the degree. And one thing that is true, which they also analyze in the paper, asymptotically, this is better. So if we look at the asymptotics of the double decomposition technique, it's better than the previous technique. But unfortunately, we are working in a very limited set of parameter ranges, and we're also working with underlying hardware. And so one of the issues we run into with the double decomposition technique is that for optimal computational complexity, you have to choose the number of decompositions very large, so essentially as the number of primes. But for optimal memory complexity, we have to choose the number of decompositions very small. And in fully homomorphic encryption, we constantly have this push and pull between, are we compute bound, are we memory bound? And on CPU, if we run this single-threaded CPU, we're mostly compute bound, but as soon as we move to GPU or even, let's say, FPGAs and ASICs, we become memory bound very, very quickly. And so this is a problem, right? Because now we suddenly have to figure out for a platform what works the best. And we have this kind of push and pull between the parameters compared to before, where we can simply choose the smallest number of decompositions, and we gain best complexity for both worlds. And so we updated the comparison. One of the things that the original paper on the double decomposition technique did is choose the same number of decompositions, no matter the technique and no matter the setting. And essentially what we did with our analysis is to show if we employ this in a real-world setting, we don't choose the same number of decompositions, we choose the optimal number of decompositions in a certain setting. And so these are amortized running times for the different degrees. Obviously, like larger degrees are slower in absolute terms. And we can see that for the most part, as soon as we have like a few primes to play with, to include into our extension modulus P, we gain speed in the single decomposition technique. So the way you have to think about this is like here at the edge, essentially, we only have one prime to choose for P. And then here at the next step, we have 2 primes to choose, 3 primes to choose, and so on. And so the less primes we use in our ciphertext modulus, the more primes we can use in our extension modulus. That is the essential idea. And if you are really like limited in the number of primes you can choose for that, the double decomposition technique can be better. But as soon as you, let's say, choose 2 primes, which is what we have in most parameter sets that we, for example, use internally at the company, or that are also in the literature, then the single decomposition technique is much better. And this goes back to we are in this parameter range, and even though the asymptotics suggest to use the double decomposition technique, once we actually focus on the parameter ranges that are currently in use, this sadly doesn't hold up anymore. We also ran this with an internal backend on the MacBook M3 Pro, where we have faster absolute execution times, and so a different platform. There we can see that the pictures is even more in favor of the single decomposition technique, and only this one data point essentially where the double decomposition technique is better. And so to summarize this, I would say these are slightly opinionated, but use the single decomposition technique with a slight asterisk, right? There are exceptions, as we've seen on the slides before. I will say this also depends heavily on your implementation, the underlying platform, right? We've talked about the previous benchmarks you saw where single-threaded CPU, if this runs on a GPU, it is very different because suddenly this trade-off between computational complexity and memory complexity comes into play that is not there on CPU necessarily. But we've run this internally on GPU, and it gets worse. Then I would also say choose the number of decompositions as small as possible, given a polynomial degree and the modulus, right? So don't do 3 to 5, go as small as possible for your parameter set. And then also consider increasing the degree. This depends on your use case. We saw the theoretical thresholds. In practice, this is obviously different. But if you are focused on throughput especially, increasing the degree also gives you more slots. So depending on your use case, you can achieve a much better throughput, and increasing the degree can actually result in better key switching parameters again. And with this, you can improve your computations quite a bit. If you're interested in the open source version of this code, this is available on GitHub. So just take a look. There's also all the data sets. There's a small program that generates all the figures and tables so that you can also take a look at the absolute numbers of this. And if you're interested in the details in the math, just take a look at the paper. I tried my best to explain key switching in an approachable way as well. And with that, thank you very much. And if you have any questions, feel free to ask here, offline afterward, or via email later on. Thank you very much.
Thank you. Right, we have time for a few questions. Don't be shy. So, I was going to ask you about this, the observation you make on compute bound versus memory bound.
Yes.
Right. And you mentioned, you said CPU was compute bound and FPGA tends to be memory bound.
So everything except CPU in what we observe in practice is mostly memory bound. So on CPU, even something like a modular multiplication, depending on the CPU, depending on the implementation slightly, can be compute bound. But as soon as we move off of CPU or even to multi-threaded CPU already, we become memory bound. Yes.
Okay. And your reference implementation is for?
This is well, so it is for CPU, but it provides a like the backend can be swapped out essentially. And so we also ran this internally with our GPU backend at CryptoLab, and also there the signal decomposition technique performed much better.
Okay.
So yes, but this is not publicly available, unfortunately. So yes.
No real argument for double decomposition technique is.
No, I mean in edge cases, I would say, right? Like trying it if in very specific parameter settings, but then it's also a cost or like a question of implementation costs and maintenance costs and all of that. So yes, but for the most part, use the single decomposition technique is true. I love the technique; it's very cool. And if the parameter ranges changes, then this might also change. But yes, for now, it's a good idea to stick with the single decomposition.
Yeah, thank you. Question?
Thanks for the talk. I was wondering the reason behind that the double decomposition technique is better performance, have a better performance for degree number about 14,000. What's the reason behind this?
I mean,
this figure, yes.
Yes. So the reason the double decomposition technique performs worse is because if you simply count the number of entities, it is more in the relevant parameter ranges. But asymptotically, it's better. But with the degrees and with the decomposition numbers and the number of primes that we are using essentially in homomorphic encryption, we never reach these asymptotic complexities. So the ideas in the paper are totally valid and it works out, but like for the parameter ranges we care about, it's not true, essentially.
So this is the limitation because the memory bound?
I mean, in this case, for these figures, they are single-threaded CPU, so it's most of that is compute bound. Although there are some aspects that can be memory bound, like something like an addition or something is memory bound as well on CPU. But for the most part, this is limited by compute, especially with the entity.
I see it. Thank you.
Thank you. Question?
Hi, thank you for your talk. I'm wondering, please correct me if I get it wrong. Like you are suggesting we should use a small number of decompositions, which is omega, but from my understanding that will hugely infect the depth of multiplication in implementation. So we might have to go for bootstrapping earlier with this kind of setting. So would you suggest that we have to use higher degree for this kind of things?
I mean, so bootstrapping, it makes things slightly more complicated. So the first thing I will say is if, like, especially here, if you spare 2 primes or something, right, or even here, you already see massive gains in the runtime performance. And the metric that we're mostly interested in is, so the number of effective levels we have is how many, because there are certain primes that we also use for bootstrapping, and we can use more primes for bootstrapping, then we get like a faster bootstrapping in absolute terms, or we can use less primes for bootstrapping, then it's slower, but we have more levels left. And so the metric that we are usually optimizing for with bootstrapping parameters and parameters in general is bootstrapping time per level remaining, let's say, right? So let's say you have 7 levels remaining, and then you want to, like, you optimize for that. And so the same thing is true for key switching parameters once you talk about bootstrapping. If you add 1 more prime and you reduce essentially the number of bootstrapping time per level spent, then that's good. And if you use too many, then it's not a good idea to do that. So there are certainly, I would say, if you look at this down here, there are certainly diminishing returns at some point where you're like, you don't want to shift more primes into this when you design bootstrappable parameter sets, but at least a few primes is worth it. And yeah.
So is your point that we should always use a small number of decompositions like the original CHES paper?
The answer is, unfortunately, it depends. Yes,
Okay.
For leveled parameter sets, yes, definitely, if you can. For bootstrappable parameter sets, it becomes more complicated, but you want to keep it in mind, right? That reducing the number of decompositions gives you runtime benefits, but as you said, it also reduces the number of effective levels you have. And you, in the end, you want to optimize for bootstrapping time per effective level.
Okay, got it. Thank you so much.
Great, thank you. Last chance. The speakers will be available after the session as well. So then this concludes the session. Let's thank the speakers.